Hello, and welcome to Maths on the Move, the podcast from plus.maths.org. I'm Rachel Thomas. Now, I've been having a lovely time this week working on an interview we did with Yang Wei He from the London Institute of Mathematical Sciences. And the interview with Yang was all about the fascinating connections between physics and maths. And I'm still working on that interview, so it should be in your podcast feed in the next few weeks. But one of the reasons it's been so much fun is how the most surprising mathematics appears in the most unexpected of places. Now, one example of these appearances is that the ideas of Srinivasa Ramanujan, the self-taught mathematical genius from India, appears in the descriptions of properties of black holes. Now, this just seems crazy because black holes weren't even a glint in a physicist's eye when Ramanujan came to the UK in 1914, and where he formed this remarkable collaboration with the British mathematician G.H. Hardy. But the maths that Ramanujan was doing, that he did in the UK, has gone on to have some really very surprising impacts. So in this week's episode, we're revisiting an interview we did with the mathematician Ken Ono back in 2018. Now, Ken was talking to us at a scientific meeting at the Royal Society to celebrate the centenary of Ramanujan's election as a Fellow of the Royal Society. His election as a Fellow, which happened in 1918, was really remarkable. He was a self-taught mathematician. He was working as a clerk in a post office in India when he wrote to Hardy at Cambridge, and how someone with so little formal training, who had actually devised their own way of writing maths that other mathematicians, they'd never seen anything like it before, how someone with that background could become accepted as one of the greatest mathematical minds of his time. Well, it's one of the greatest stories in maths. And the important thing, the reason he was elected as a fellow, is that his mathematics, as well as his personal story, was truly remarkable. So we revisit our interview with Ken back in 2018 by starting off with the question, what was it that made Ramanujan's maths so exceptional?
Ramanujan had a gift for formulas. Most of us in mathematics build theories, or there's a conjecture that we're trying to prove, and we're trying to solve problems. This was not how he did his work. He believed his ideas came to him as visions from a goddess. The formulas were zapped into his mind, and the formulas he recorded he thought were beautiful for whatever reason. And as you have seen in some of the lectures today, particularly the first two lectures by Professors Berndt and Andrews, people have spent their entire lives working through and not only confirming Ramanujan's formulas, but also they've tried to build theories from these glimpses of formulas. So what is it that people saw in Ramanujan when he was alive that resulted in his election? Well, together with Hardy, they proved these incredible formulas that tell you how many partitions there are of an integer n. And at the time, that was considered an impenetrable problem. So the fellows that elected him were almost certainly astounded that such a formula not only existed, but could be proved. I'm pretty certain that formula alone formed most of most of the citation for his election. But make no mistake, that's now a very small part of what has grown to be his legacy. But at the time, he was probably known as the Wizard of Formulas, but his election was almost completely based on this problem of the partitions that was considered hopeless.
And that's sort of surprising to people who hear about that to start off with. It's an area of number theory that's so easy to explain what a partition of numbers is, and the fact that it was such a difficult question. Can you just tell us what you mean by partition of numbers?
Sure. If we were to express the number 3 as 3 along with all of its representations as sums, it's quite easy. There's the number 3, there's 2 plus 1, and there's 1 plus 1 plus 1, and so there are 3 ways of partitioning 3. It's also easy with 4. 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1, and 4 ones. There's 5, so if you counted like I was with my fingers, there's 5 partitions of 4. So as easy as it is for anyone to follow the process, the total number of partitions for larger and larger integers becomes impossibly difficult. Try to repeat just what we just did a moment ago with the number 10. We can start 10, that's the first one. 9 plus 2, 9 plus 1, sorry, that's the second one. 8 plus 2 is the third one. 8 plus 1 is the fourth one. By the time you get to 10 ones, believe it or not, you should have counted 42 different ways. So even trying to imagine this process for a number like 20 probably is quite formidable. So what Ramanujan did with Hardy was a formula that doesn't necessarily give the right answer, but it's really, really close. And it holds for all n. And you can just plug in for n, and you basically get back the answer. And for mathematicians, just like I just described it to you, it would have been, God, it's an obvious process, but we don't know how to count how many outputs the process gives. Someone has to be pretty crazy smart to figure out a shortcut so you never had to count. So I think you can see why that's astonishing.
Yeah. Definitely. Now, one of the things the first 2 lectures were on, we're talking about his notebooks. What are those notebooks, and why are they different from the sort of work of mathematicians that we would have normally had?
So the first 2 talks will stand out as being very different from all of the other talks. All of the other talks will be more along the lines of professional computer scientists, professional mathematicians, and professional electrical engineers. It's what we do today. We are celebrating how Ramanujan's formulas or his ideas have inspired us for contemporary science. The first 2 talks were very different. So George and Bruce are the 2 world leaders, the 2 world experts on Ramanujan's formulas. And in their words, you hear him saying, we wish we understood how Ramanujan came about his formulas. So their work, which has spanned decades, is complicated by the fact that, and I think you heard this, Ramanujan didn't use notation that anyone else in the world ever used. So the way to think of the results in the first 2 lectures and that challenge in general wouldn't be very different from an historian who studied ancient Greek literature. So you would want to somehow find some archive someplace where there were documents that you could study, but of course there's this not only language barrier, I mean there would be many barriers to trying to interpret anything from centuries ago. That's what you should be thinking in terms of the challenge of making any sense out of these notebooks. And Ramanujan did write 30 papers when he was in England, and they were professional papers, which already says quite a bit. When Ramanujan arrived here in England in 1913, he knew nothing of modern mathematics. He made mistakes all the time. But somehow very quickly, within a span of a year to a year and a half, he was formally trained. He was very smart, so he could catch up very quickly. And so the papers he wrote here, by every professional standard, were world-class papers. So that is also a testament to how gifted he was.
So given that he was able to use both, he started off using this non-standard notation, and then he did end up writing in sort of more accepted notation. Mm-hmm. I mean, what was it? Was there anything using this non-standard approach that he started with that gave him some advantage or some different insight, perhaps?
Oh, absolutely. In fact, this is not just Ramanujan, right? This is actually something that we should do a better job in schools, which is part of the reason we're having this Spirit of Ramanujan initiative. A good student, it's good to be a good student, right? You want to master topics that are taught in school, and you become an expert and you become proficient in them. The world needs these people. But what we also need, and it's easy to forget, but extremely difficult to train, perhaps impossible to train, is that the world needs people who will propel human thought forward. Just being a good student doesn't mean you propelled thought forward. It means you become a master technician. People still win Nobel Prizes for confirming theories predicted by Einstein, right? So there are from time to time these brilliant people, think Einstein, think Newton, think Ramanujan, who come along, with ideas that support generations of scientists. So what is it that is in these formulas? Well, not only is it that the case that these formulas have given people like Andrews and Berndt decades of work, it's also that these formulas have offered glimpses of theories that Ramanujan probably wouldn't have been able to articulate himself. Theories that nobody needed until they needed them. So, for example, tomorrow there'll be lectures about black holes that make use of some of Ramanujan's mathematics that nobody even knew that a black hole was something to study when Ramanujan was alive. But he had already developed some of the first formulas that would be used to explain their properties. What's astonishing is that Ramanujan has done this for us several dozen times. And so, where does that genius come from? I don't use the word genius very easily, but make no mistake, if you write down formulas that you find beautiful and important for some reason, so important that they have earned a spot in your notebook, nobody else knows why they're important until decades later they realize actually studying multi-centered black holes depends on an equation. I wish somebody had come up with it, only to discover that they're already in some mysterious notebook. There's something quite spiritual.
That was mathematician Ken Ono talking to us in 2018, leaving us with that tantalizing glimpse into the mathematics of Ramanujan. And if you're keen to know more about how his mathematics helps us understand black holes, as Ken mentioned, stay tuned for the upcoming podcast featuring our discussions with Yang Weihei. And in the meantime, you can find out more about Ramanujan, his life and his mathematics and their impact by going to plus.maths.org and searching for Ramanujan. We'll put a link in the show notes. Thanks for listening, and bye for now.